member of Academic Council, member of the Faculty Board, Science and Engineering, Vice Chancellor's nominee to the Board of Secondary Education, and so on. So with this brief introduction, I welcome Dr. Anggur Bharali to this first session, and he will be speaking on the topic linear algebra and its application in data clustering. So with these few words of introduction, I now welcome Dr. Anggur Bharali to take your time and give your talk. Thank you, sir.
Hello, sir. Are you online? Seems you are having some network problem now, sir.
Yeah. Am I audible?
Yeah, yes, sir. Now you are audible.
Am I audible?
Yes, sir.
Okay. There is some issue with the network connectivity, I guess. Yeah. Anyway, thank you for the invitation. I would like to thank all the for inviting me to talk in particular webinar. Familiar as properly this some basic clustering in the process. We'll try to see how these issues with data clustering can be overcome using Am I audible?
Yes, sir.
Okay. Can you see my screen? Can you see my screen?
Yeah, yes, sir. We can. No, we can see your slides also.
Okay, 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 okay. So the topic that I'm going to discuss is the application of linear algebra in data clustering. So it will be divided basically into three parts. First, we will try to introduce what is data clustering. Then we will try to see some basic application of linear algebra in data clustering. And if possible, we will go to the advanced application of linear algebra together with graph to cluster data into communities. Okay. So the introduction of clustering, as we probably most of us know that clustering is basically dividing a given data set into some groups with similar features. Okay. So clustering helps to split data into several subsets. Each of these subsets consists of data objects with higher intersimilarity and low intersimilarity. That means within the group, the similarity will be high, and between the groups, the similarity will be low. Okay. Now, before going into the clustering technique, we should learn that how the things are learned by human being. So there are basically uh, two broad, we can say, classes of knowledge acquiring. One is the method of declarative knowledge. The other one is the method of imperative knowledge. In declarative knowledge, basically we read out, we try to remember the things, we try to collect the facts, and we just try to remember these facts. In imperative knowledge system, what we try to do is that we try to observe things, we try to collect data, and from the data points and from the what I should say, from the knowledge we have gathered from these given data, we'll try to interpret some other conclusions which are not listed as facts. So basically, imperative knowledge system is the base of what is called the imitation game. So data clustering is basically based on the fact that from the very basic imitation game, we will move towards the real thing. Okay. So what are the steps involved in imitating something? So there will be some training data. Some data will be given to us, and based on this data, we will try to figure out that what will be the generalized form. Then we propose some generalized form, and again in the third step, what we'll do, we'll test this particular model, whatever we have come up with. Some data points will be tested, and if that model can sustain, then we will accept it. So these are the three basic, I should say, paradigm in learning or developing a model to understand some data points. And based on the understanding of these data points, we can cluster the data points. Because without having any knowledge about or the features about the data points, it is not possible for us to divide them into groups. Okay. So let us consider one example. Okay. So here, suppose I'm considering here the New England Patriots. It's a football team, and based on their name, height, weight, positions are leveled. So we are considering basically two positions. Am I audible? I hope my slides are visible.
Yes, sir. Yes, sir. It's visible. You're audible.
Okay, okay. So it's going well then. There are some issues with my network connectivity. Anyway, so two positions are considered. One is receiver, the other one is lineman. And with the given kind of labeling, we know the players where they are labeled. I mean, who of these players are receivers and who of these players are linemen. I know this. And also we have the data points of the name, height, and width for each of these players. But if we don't have this kind of division, I mean, the classification of receiver and lineman, and if we simply have the data points only, is it possible to divide them into two groups? That is the point, and that is the basic idea of data clustering. We have the data points, we don't know anything about these players, and our objective is to find out which of these players are actually lying in the receiver end, which of the players are lying in the group of linemen. Okay, so these are the data points. Based on height and width, we have these data points. And basically, we'll try to figure out that what will we say based on the average. I mean, based on the average weight, if I want to divide them, it will be something like this. So these data points, so these points are basically, so these points are basically some players. Okay, these data points are related to some players, and you have a division line. So I can say that these players are linemen, these players are receivers. Okay, but that is not true, because you can see that some of the receivers are there in the lineman group, and some of the linemen are there in the receiver group. So we go with another criteria, that is the height. So what is the average height? So based on the average height, we divide the players. There also we can see that the group that we are having based on the average height is not going with the two groups that is given to us, that are given to us. Okay, then we try something like this. Here we are considering both height and group, height and weight, and based on that we have this kind of division. Now we are happy with this division because this division is going with the given information that we have. I mean, this group is a lineman, this group is receiver, something like that. But once you have this model, now you are interested to test whether some additional data will fit into this or not. So this is the group, actually unlabeled group. So this is the label group. That means it is given that these points are linemen, these points are receiver, something like that. Okay, this group are given as per the labeling. But here we are not considering the labels. We are trying to figure out that whether that labeling can be actually done based on the features of this, or can we model these data points based on the features so that this kind of labeling will be possible without actually knowing the position of the players. Okay, so based on the labeling, this line will be a better choice for division of the players. I mean, below this line, these players will be like receivers, and above this line, these players will be like linemen. But here is a catch. If we test this particular model, you can see that we are adding two new data points, blonde and white. So with these data points, you can see that these data points are there in this group with this line. With this line here, these points are lying in this group. But for some reason, we know that one of these guys is not actually in this group, rather it should be in the other group. So the line that we have based on the level itself is not correct. So you can see that based on some leveling also, we may get may get wrong information about the data set. So what will be the solution to overcome this kind of issues? So whatever line that we have drawn from the unlabeled data points, you can see that 2 points are again lying on the other group. So this line that we have developed is not good enough to divide the data points into some groups. Okay, let us consider another example. Suppose I have some features about some uh, little, and you have to decide whether that is a reply or not. So basically, our idea is to find out the based on these features, what are the features that we are considering are egg-line, skulls, poisonous, cold-blooded, whether it has legs or not, or if there is some leg. If that creature has legs, then how many legs are there? So based on that, we are trying to figure out that whether we can have a model for a reptile. So now the first data point that I am considering here is the cobra. I know that cobra is egg-line, it has skull, it is poisonous, it is cold-blooded, and we know that it is reptile. It is known to us. So with this, can you have a model? We don't have enough information to figure out that what are the criteria which will tell you that it's reptile. So to do that, we will get one more. Again, rattlesnake it is poisonous, cold-blooded. From these 2 points, there was we can conclude that reptile is that will be egg-line, pulse is poisonous, cold. So that is model. Now what we have this model? Other. Suppose we have one upon like boa constrictor. It is not egg. It has scars. It is not poisonous. So you can see that my model is not device model. Device model say that so constant model will get with some other. Okay. So not be so yeah this thing is to come uh, uh, is is not not die. From say test go come with because
Hello, sir. We are having some problem with your voice, with your audio.
Am I audible?
Yes, sir. Yes, sir. You are audible.
Okay. So I don't know where I should. I mean, I should resume from. So let me go back to this example. Is it okay? Is it visible?
So we are not able to see your screen. Your slides are not visible, sir.
Can you see my screen?
So can you try? So some network issues going on with the resource person. So let's wait for some more time.
Am I audible?
Yes, sir. You're audible.
Can you see my screen?
Yeah.
Can you see my
Yes,
screen?
yeah, it's
Yes,
visible.
yes.
Okay, okay. Uh, so there is some real network issue here. Anyway, so let me start from the second example. So here we are basically looking for a model uh, that will be that will give you or that will help us to find whether a particular creature is reptile or not. So the first data point that we have here is cobra. It's a reptile, and we have considered some features like egg line, skulls, poisonous or not, cold-blooded, and how many legs are there. And with this data point, we cannot initiate a model. Why? Because we don't have enough information. So next, we try one more data point, that is rattlesnake, and we know that rattlesnake is egg-laying, it has skulls, it is poisonous, it is cold-blooded, and it's a reptile, right? So we are considering basically reptiles and trying to figure out what are the features which are required to be a reptile. So this is our initial model based on these two data points. We can see that in both the data points, these creatures are egg-laying, has skulls, is poisonous, cold-blooded, and has no legs. So that is our initial model. Then we try this model for skull 1, poisonous 1, cold-blooded 1, leg 0. So this is the vector that will associate with cobra. For salmon, if you consider, so this is not a reptile, so we will not consider this. For alligator, if you consider, what will be the feature vector? Feature vector will be like 1, 1, 0, 1, 4. So this will be the feature vector. So you can see that we can associate some vector to these features. So these vectors are called feature vectors. But there may be some issue with the feature vector, and based on these feature vectors, we can actually cluster these data points. How we will do that? It is based on the distance. So this is what I am saying, that we can construct or we can come up with some vectors. So here this feature is not binary, that is creating the issue. Anyway, we'll try to figure out. So now let us consider two very basic distance metric. One is Manhattan distance, the other one is Euclidean distance. And I hope these distance are very, I mean, we all are comfortable with this distance metric. So based on this distance metrics, what we can do is that we can figure out that what is the distance between this vector and that vector, right? So if we plot this vector points and try to figure out the distance between them, we can see that this will be the Euclidean distance between the animals. So rattlesnake, the distance between rattlesnake and boa constrictor will be 1.414. Rattlesnake and dart fork will be 4.243, something like that. So from this, what you can see is that dart fork is far from boa constrictor. So it is better to put dart fork and boa constrictor in two different clusters. So we have to decide what will be the, what is the critical distance? What is the critical distance for these data points, based on which we will divide the clusters. If that distance between these 2 points exceed that critical value, then we'll put it in some other cluster. Otherwise, we will put them in the same group. So this is the basic idea how we can use linear algebra in data clustering. Okay, so if you like that, I'm taking this example from this particular site. If you are interested, you can go to this site and you can revisit this example. Okay. Anyway, so what are the issues here? What are the issues? Let me check the table again. Here you can see that alligator is closer to dart fork. Alligator is closer to dart fork than snake. Rattlesnake. So why this is happening? Because of this feature actually, right? But we know that alligator, the features of alligators are more closer to dart snake rather than dart fork. So these distance metrics or these feature vectors are actually not giving you a proper picture of the communities or the clusters present in the data points. So we can see that though this method is theoretically okay, but there are some constraints. What are the constraints? The constraints are, what are the features that we should consider? Here we are considering features like egg-laying skulls, poisonous cold-blooded lakes. So whether there is any other feature that is helpful to actually distinguish these creatures that we have missed. So feature vector, the feature vector is a very, I should say, tricky topic. Which features we should take, which features I should drop. So features engineering will tell you that which features are actually relevant and which features we should take, which features we should ignore. Also, the choice of distance metric is also important. You can see that this this value of this distance metric may be different if we choose different distance metric. And that may help us to find clusters in a proper way. So issues of concerning when learning models. So when we learn through the models to cluster data points, distance metric between the data points is very important. The choice of the distance matrix, the choice of the feature vector is also important, and there are some complexity in the model. Like how many groups are actually there? We may not know how many groups are there. It is helpful to us if we know at least the number of groups there in the data points, but that is not always the case. Suppose we have 100 or 1000 data points and we have to divide these data points into say 5 groups, 6 groups. So if we know that we have to divide it into 5 groups and there are some 5 communities present in the data, in the entire set of data points, that is helpful. But if we don't know that the specified number of clusters, then there may be some issue. We'll try to see what are the issues and the complexity of separating surface. Like we can consider a straight line, we can consider a circle, we can consider a 2-dimensional hyperplane, or you can consider a higher dimensional hyperplane as the separating surface. And there is another issue of overfitting. So what is overfitting? Basically, we are considering more features than required. That is overfitting. And we consider more, you can say, data points than we should actually consider. Okay. So these are the clustering approaches and the issues. Here you can see that the issues, as we can see, that how do you decide the best number of clusters? That is a very big issue. And how do you select the best features? So these are the main issues that we can think of in case of data clustering. Then what is the option? What is the option? That how can we overcome these issues? I mean, the number of clustering and the choice of best features. How can we come over these issues? So one such solution is the spectral clustering. So where we need not have to know how many clusters are actually there beforehand, or we may not have to know that how many features we should consider. Okay. So what is spectral clustering? This clustering is basically a method based on graph theory. But you can see that this clustering technique can also be used for non-graph data points. I will tell you how can you do it for non-graph data points. So how much time I have? Because I have lost 10 minutes or so in between. So can I continue for 10 minutes more?
Yes, sir. Yes, sir. You can continue.
Okay, okay. So this spectral clustering is again based on eigenvalues of different matrices. And I know that eigenvalues are associated with matrices, and it is a part of the theory of linear algebra. So these matrices are built from the graph or from the data sets, and we use the technique of linear algebra or the theory of linear algebra to actually develop this clustering. So first we'll try to figure out how can you do this for graph. Then we'll see how can you do this for non-graph data points. So suppose I have a graph, then corresponding to this graph, I can draw or I can have a matrix known as a Laplacian matrix here. So L is the Laplacian matrix. How can you construct this? You can see that all the diagonal points are basically the degree. What is degree? Degree means how many edges are incident on this in this node. So these are called nodes, these are called edges. Now how many edges are incident on this node? That will be the degree. So you can see 2 corresponding to 1. Corresponding to 2, you have 2 because corresponding to this vertex, 2 edges are incident on that. Corresponding to the third vertex, you have 3 edges. That's why it is 3. And corresponding to 4, you have only 1. So this is 1. And what about this -1 and 0? So you can see that if there is no connection, then I put it 0. So between 1 and 4, there is no connection. That's why it is 0. If there is a connection, like between 1 and 2, I have a connection like -1. I will put -1. I have a connection between 1 and 3, I should put -1 there. Obviously, if the graph is non-directed or undirected, it's an undirected graph, so matrix will be symmetric about the diagonal position. Okay. So if this is -1, that will also be -1. Also, if we closely observe this matrix, we can see that sum of each row is equal to 0. Sum of each row is equal to 0. And from the theory of linear algebra, we know that if sum of each row is equal to a fixed number, then that is an eigenvalue of the matrix. This is from the theory of linear algebra. So 0 is always an eigenvalue of the Laplacian matrix. So Laplacian matrix is always singular. It's a singular matrix. 0 is always an eigenvalue. Also, since it is a real matrix and it is symmetric, so eigenvalues are real. Eigenvalues are real. Eigenvalues of this Laplacian are real. So these two observations that we will consider from this example, and we'll try to, I will basically try to explain this spectral clustering, if it is possible for me, in 5 minutes of time. So let me go to yeah. Wait a minute. So can you see my screen now?
Yes, sir. Oh, it has gone off again, sir.
Okay. So can you see my board now?
No.
Is it visible now?
Yes, yes. It's visible now.
Yes. Oh, yeah. So basically, we know that Laplacian matrix is L is symmetric and it is singular. So also L is positive definite. It's a positive definite matrix. So from this, what you can say is that all the eigenvalues are non-negative. I should say semi-positive definite. And this can be proved from the fact that L is actually equal to Q transpose Q, where Q is called the incidence, directed incidence matrix or oriented incident matrix. And if we consider some vector like this will give us Q transpose T whole square. So this is something like this, right? Now all the eigenvalues are positive, and we have a matrix with real eigenvalues, and I know what is the lowest eigenvalue, that is the 0 eigenvalue. So I can list the eigenvalues of L to be 0, like lambda 2, lambda 3. If we have n vertices, then it will be something like this. Here the second eigenvalue is very interesting. This is known as algebraic connectivity. Why? Because this eigenvalue will tell us whether the graph is connected or not. Connected or not. Even the graph is connected and we have low value of lambda 2, that means that there is a tendency that the whole graph will actually be divided into two groups. There is a tendency of the graph to have to get disconnected because this value is very low. And from this particular observation, what you can see is that if there are some communities in the graph, the entire graph may be connected, but I can find out the disconnected, or I should say the components of the graph from the value of lambda 2, because corresponding to this value there will be some eigenvector, say let me call it x2, and these eigenvectors, these values will be either positive or negative. And the best thing is that corresponding to this magnitude, or sorry, the sign of the values of these eigenvalues, I can divide these points. Like corresponding to 1, say it is positive, then I should put it in this group. Say corresponding to 2, this is negative, so I should put the second data point here. Corresponding to 3, say it is positive, then I should put it here. Say corresponding to 4, it is again positive, then I should put it here. Then corresponding to 5, say it is negative, then I should put it here. So here you can see that we need not have to know that what are the features. Rather than based on this eigenvector, we can classify the data points. So all these data points will be in this group, these data points will be in that group. Remember, if we want to have more number of clusters, we have to repeat this process in a similar manner, and that I will not discuss because that will take some time. Here just I want to conclude this talk with the observation, or with the idea how to convert non-graph data points to graph data points. Like suppose I have some points which are not points of or nodes of any graph. So how can you construct a graph out of it? Because here you can see that we are developing this theory only for graph, and we have we have mentioned earlier while defining or while introducing the spectral clustering that this particular technique can also be used for non-graph data points. So if we have some data points which are not connected, so basically we have to first construct a graph out of it. How can you construct a graph out of these data points? So basically what we can do, we can arbitrarily connect this point. One technique may be this, and that will be very primitive, very raw, so we will not consider that. What we will do, that we will try to figure out, or we will consider any distance metric, arbitrarily choose a distance matrix and try to join them based on this distance matrix. Say I will consider, say if the distance between this point and that point is less than some given number, say L, then I will have a connection. If this data point is far from this data point and the distance between these 2 points are greater than L, there will be no edge. So you can see that from some given data points, we can even construct a graph based on some distance matrix. So what is the advantage? here the choice of distance matrix is not going to play a big role to find the clusters, because clustering will be based on the technique of spectra, or based on the spectra uh, of the matrix that is associated with the graph. Of course, it will play some role, but it will not be vital. The role of the choice of the matrix will not be vital. Also, the choice of the feature vector is not going to be a key factor in spectral clustering. So with this introduction to data clustering, I would like to conclude uh, my talk today.
Okay. Thank you so much for.
Yeah. So these are the references. If the students are interested, because as I'm told that most of the, the target group will be the students. So I'm suggesting these two basic books. One is, the first one is a book. The second one is a paper, which is a basic paper on spectral clustering. If anyone is interested, they can consult these two references.
Please share your screen, sir. Your screen is not visible now. Hello.
Yes.
Yeah.
Can you see my screen?
We can see
you
your
see
screen.
now?
Okay.
Yes, it is
Got
coming.
it now, sir.
Oh. So actually, I'm having a real issue with the internet. The Zio is not working. So I'm trying via some other connectivity. Sorry for that. I have taken a lot of time.
That's not a problem, sir.
Okay. Thank you. If you have any query, I'll be happy.
Okay, thank you so much, sir. And then it was a very
I'll be happy
informative
to
session.
address.
So now I would request Mr. Sedevico Chase, Assistant Professor, Kohima Science College, to take over for the Q&A.
Thank you. Thank you, Sabandan. And thank you, Sir Ankur, for a very enlightening and very interesting talk. If there is any queries from the student side, participant sides, you may write in your chat box or raise your hands, or some of us are watching through YouTube also, so you can type your query from the
yeah, or you can drop mail to this particular address. I'm sharing my mail ID. Yeah.
That is very kind of you, sir.
Yeah. So if you are interested, then please drop a mail. I'll be happy to reply. You may not have a question right now, but
Yeah.
I'll be very happy if you drop a mail. Yeah.
Thank you. We will note down the email, sir.
Thank you.
Yeah, unfortunately, there were some network issues, and maybe
Yes.
with the help of data clustering and linear algebra, we can improve those network issues in the future.
Yeah.
So if there is any questions
Sorry
from
for
the
that.
participant side, we can take them. Sir will be happy to answer them now also. Or like he has already shared his email address, if you have some queries, you can always mail him. I think he's welcoming us to mail him. So
Thank you.
yes, so
Yes.
one more thing, when we are still waiting for questions, if there is any, what are the research avenues or research opportunities in this field, data clustering, linear algebra?
Okay. So here you can see that there are so many issues. The prime issue is the selection of the matrix. The second issue is the selection of the features. So there is, there is no well-defined technique to choose the metrics. There is no well-defined technique to choose the features. So it's like a trial and error technique. So there are so many methods in data clustering. Whichever is suitable, whichever will work, we'll consider that. It is something like this. But if we consider the, the theory of graph, there we may have a solution. So spectral clustering is one such solution to these problems.
Sir.
Yeah. Yes.
So cool is now. Yeah. It's like this. It's one eye. He's here. One eye. What is this?
Hello.
You are not audible.
Last question.
Is there any question? It is not audible.
No.
Your voice is not clear.
How do you let it be?
I think they're talking.
So anyway, basically, graph clustering can be one of such solution. I don't know, because again there are some issues in data clustering. Like if we have, more number of clusters, more number of communities, this technique is very cumbersome because you have to divide these communities in a, I should say, binary way. In each step, I can divide the community into two parts. So in that way, if you try to proceed, suppose there are 100 communities, then this algorithm will be very costly. It will be very time consuming. So these issues are there. If you can come up with some other solutions, then I think there are so many. So because these issues are primarily related with the data science, and we know that data science is the current booming topic that we have. And people are working. There are some other computer-based technique to cluster this data, like k-means, that can be helpful. This is again based on, the idea is based on linear algebra. There you find some means, like k number of means. Again, you have the same issue that you must know that how many communities, what will be the value of k? How many communities are present in that particular data set? How many clusters are actually there? So you should, beforehand, you should know that how many groups you have to form. That is the main issue. If you don't know that how many groups you have to form out of these data points, it is not easy to execute methods like k-means. Because k is the number of community you are looking for. If you don't know k, then you are gone, you are in soup. So basically, these are some of the issues, and I hope that people will take up, and people are working on it. They are, proposing better techniques, better advanced techniques for data clustering. Yeah, thank you.
Hello.
Yes.
Thank you, sir, for your very informative.
And sorry for the disturbance.
No problem, sir. No problem. This happens.
Can't help it. Yeah.
There is no problem in that. Surely, it is bound to happen. Just, sir, one very small question.
Yeah.
Sir, what is the basic topic required at the MSc level? What is the basic topic is required at the MSc level as a specialization for going to the research in this field?
It's a very pertinent question. It's a very good question. In fact, I think the basic idea of linear algebra is good enough. If we have good knowledge of linear algebra, that is good enough, because whatever techniques or whatever notions of graph theory that we are considering, that we can take up later. No issue about it. But if we have some introductory course in graph theory also, that may be helpful. But I think with the help of linear algebra, we can deal with that.
Thank you.
Yeah.
Thank you, sir. Understood.
Thank you so much, sir. And we look for your support in the future also, in the coming days also.
Yeah, I'd love to be here.
Yeah. And if there is no much queries from the participant side, I think we will move on to the next session. Thank you so much once again, sir. I hand over time to Sir Bandang Wapang again. Thank you.
Okay, thank you so much. In fact, we were expecting a more interactive this Q&A session, but maybe all the participants they are reserving for the last session. So let's hope that the last session will be more interactive. And thank you once again, Dr. Barali, for the wonderful session. So let's move ahead to the second session. So I request Ms. Tamjun Naro, Research Scholar, Department of Mathematics, Kohima Science College, to introduce the second resource person.
Okay, a very good morning to each one of you. I would like to take this time to give a brief introduction about our resource person for the next session. Dr. Nobal Kanta Sharma, Assistant Professor, Assam University, Silchar. His areas of interest are number theory, algebra, graph theory, fixed point theory in distant spaces. He completed his post-graduation from Guwahati University and was the gold medalist during both his graduation and post-graduation, and was also placed among the top 20% awardee in the CSIR GRF net, and also secured the All India rank 18th position in the GATE exam. In the year 2018, he completed his Doctor of Philosophy in Algebraic Number Theory from IIT Guwahati and has over 5 research papers published in reputed journals and have also presented in both national and international conferences. He has over 17 years of teaching experience and has organized over 8 conferences, workshops, and webinars successfully. He has also delivered over 9 lectures as a resource person in various conferences and workshops. And today, he will be discussing on the topic infinitude of primes using infinite product with us. So, sir, you may please take your time.
So am I audible? Hello?
Yes, sir, you're audible.
Yes, sir. You are audible.
Yeah, thank you. So a very good morning to all of you. So first of all, I'd like to thank Dr. Pandey for his invitation to give me a talk on this webinar. So I will also like to thank each and everyone involved in this webinar. So it's a good attempt to spread the mathematics among the young students of this region. So the first talk we have seen, it was a very good illuminating talk on the applications of linear algebra. So in this talk, it will be more theory than applications, and it will be at a very elementary level, looking at the participants. So let me share my screen. Kindly let me know if it is shared or not. So are you able to see the screen?
Yes, we can see, sir.
Yes, sir.
We can see.
Yeah. So as you can see, the name of the topic will be infinitude of primes using infinite product. So since 300 BC, it is known that the number of primes among the positive integers is infinite. So Euclid give a very wonderful, a very short, elegant proof of this fact. And afterwards, Euler, another very famous mathematician, he also tried to give a proof using the concept of infinite product. So though we'll see that his proof is not fully correct with the modern rigor, that rigor is missing because in those times, the mathematics was not done exactly that people used to do in the modern days. So even though the concept of infinite series is being taught, at the undergraduate level, the concept of infinite product is not done at length. So it will give us an opportunity to see what infinite product is and how we can prove the fact that the primes are infinite using the concept of infinite products. So in the process, what it has done is that these primes are a very fundamental object in number theory. While the concept of infinite series and sum and products, they are basically objects of real analysis. So what this proof has actually done, it has opened the door for interconnection between number theory and analysis. So actually this formula for infinite product has given rise to the subject that we know as analytic number theory today. So let us, without much ado, let us start. So I am repeating, it will be at a much elementary level, and I hope everybody will be able to understand this. So the brief overview of the talk will be, I'll first revisit the Euclid's proof of infinitude of primes. Then I'll state a very elegant formula invented by Euler, and he has given a proof of this formula also. As we'll see that if we scrutinize this formula, we'll see that his proof as well as the statement of the formula were both not 100% correct. But it gave enough food for thought. After that, this famous mathematician called Kronecker, he has modified the statement and also given a proof which fits the modern rigor. To do this, to give a correct and modern formula, we have to know the ideas of infinite sum and infinite product. And then we'll give a rigorous proof of the Euler's product formula. And then finally, we'll use this formula to give a proof of that the number of primes is infinite. So let us first see a Euclid's proof of the infinitude of primes. So let us begin with the what prime numbers are. So prime numbers are basically the building blocks in the positive integers. We say that a positive integer n greater than 1 is prime if the only positive factors of the number 1 and the number itself. So we do not allow 1 to be a prime number. The reason, there are many reasons actually, and it is not a hard and fast rule. There are many famous mathematicians who were willing to consider also 1 as a prime. So among them, G.H. Hardy, everybody has heard the name of G.H. Hardy. So he was also initially willing to call 1 a prime number. Then he also realized afterwards that it is better to exclude 1. One of the reasons for that is this theorem, this fundamental theorem of arithmetic. So this theorem says what? A positive integer n greater than 1 can always be factored uniquely as a finite number of product of finitely many primes, where the expression is unique up to ordering of the prime factors. So you can easily see that if we allow 1 to be a prime number, then this uniqueness in this factorization will be lost. For example, the 6 I can generally write as 2 into 3. But if you allow 1 to be a prime also, then we will be able to write 6 as 1 square into 2 into 3, or then 1 cube into 2 into 3. So any power of 1 we can allow. So in that case, the uniqueness in the factorization will be lost. So this is one of the main reasons where the modern mathematicians are not willing to consider 1 as a prime number. So as an immediate consequence of this fundamental theorem of arithmetic, what we got is that any positive integer n greater than 1 has at least one prime factor. It is obvious from the fundamental theorem because if n is a product of prime numbers, so at least one prime factorization factor is there in the prime factorization. So that prime factor will divide the integer. So any number greater than 1, it must have at least one prime factor. So in the fundamental theorem of arithmetic, in the finite product, we are also allowing product of one factor. For example, 7. 7 is a prime number. So 7 itself is a product. We are allowing this 7 equal to 7. This 7 itself we are allowing as a product. So that thing has to be there, be allowed. Then only, or otherwise we have to just slightly modify the statement that any positive integer n greater than 1 is either a prime or can be expressed as a product of primes. Okay. So let us slightly go to the proof of the infinity to the primes given by Euclid. So this is a very ancient proof. It was he did it around 300 BC, but this is one of the shortest and most elegant proofs you will see in any branch of mathematics. So what he did, he assumed that let there be only finitely many primes. So suppose these are 2, 3, 5 up to Pn. So we also assume that we have arranged the primes in an ascending order. So then what he did, then he considered number. He multiplied all the primes up to nth, and then he added the number 1. So what we know about this number may be prime, this may not be prime. But this is at least a positive integer which is strictly greater than 1. Because that is why we have added the number 1. So see, if we do not add the number 1, this number will not obviously be prime. It will have many factors. P1, P2 up to Pn, all are factors of this. But as soon as we add 1 to it, none of them will be a factor. So this is one of the crucial observations. So this number is obviously greater than 1. And so by fundamental theorem of arithmetic, it will have at least one prime factor. Okay. So let this prime factor be P. But what Euclid assumed in the beginning, that there are only finitely many primes, and the only primes are P1, P2 up to Pn. So this new P, it must be one of those primes. So this P must be Pi for one of I. But then P will divide the product P1, P2 up to Pn, because P is one of these of primes only. And since P divides n also, because P is a factor of n, so P must also divide this n minus the product. But this is 1. So no prime can ever divide 1, because 1 is not allowed to be a prime, and any prime is bigger than 1. So no prime can divide 1. So this gives a contradiction to the fact that we have assumed that only finitely many primes are there. So this assumption must be wrong, and so there must be an infinite number of primes. So a very elegant, beautiful, and short proof. So this existed around 300 BC. So let us see now that product formula that we are talking about, which is devised by Euler, and he also gave a proof of this result. So the statement, what in the language of Euler, how he writes, the product continued to infinity of this fraction 2 by 1, 3 by 2, 5 by 4 up to infinity, in which the top elements are the prime numbers 2, 3, 5, 7, and the bottom elements are nothing but 1 less than the prime numbers. So if we go on multiplying up to infinity, then this product will be equal to the sum of the infinite series 1 plus 1 by 2 plus 1 by 3 up to infinity. And he also knew that both these numbers are infinite numbers. So this is his product formula. He has arranged a sum. The sum is 1 plus half up to infinity. This sum he was able to write as an infinite product. And he realized that they were both infinite. So in modern language, this equality will not make much sense, because both of these are infinite numbers. Okay, but at that time, at the time of Euler in 1737, this concept of infinity was not that much clear as it was now. The concept of infinity was mainly introduced more rigorously by George Cantor. But this Cantor was born only in 1845. So more than 100 years after when Euler find this formula. And Euler also gave a proof of this formula, which we shall see now. So in modern language, how the formula is written, generally this formula is written as summation 1 from n from 1 to infinity 1 by n. Then product over the primes, there capital P denote the set of primes, over the numbers, P by P minus 1. In the top there are prime numbers, in the bottom there are P minus 1. So we can divide the numerator and denominator by p. So to get 1 by 1 minus 1 by p. So the right hand side product and the left hand side sum. So this is a very wonderful formula which relates an infinite sum with an infinite product. So let us see how Euler given a proof. So he started with the series, infinite series, 1 half, 1 by 3 up to so on. Then he knew that this sum is not finite. This is called the harmonic series, and we shall see afterwards that this series is not convergent. So its sum goes to infinity very, very slowly. So although Euler was aware of the fact that this number is not finite, so he ignored this fact and he treated this infinity as a real number. Now we know that this infinity cannot be treated as a real number, so the usual rules of algebra do not apply for infinity. But at that time, these things were not very clear, and Euler ignored this fact and he treated this x as a real number. So he divided this x by 2 and then subtracted. So what he did, he wrote x by 2 as x minus x by 2, and he put the value of the x and then x by 2. Then he got all the what left is 1 plus 1 by 3 plus 1 by 5 up to so on. And then you observe that he is left with a series in which no denominator is even. So the number 2 and all the multiples of 2 are missing. Originally in the sum, all multiples of 2 are also there. But now after dividing by 2 and then subtracting, he obtained a new series in which 2 and no multiple of 2 is there. Then he proceeded further. Then he again, this new series he divided by 3. And then he obtained a series 1 by 3, 1 by 15 and 1 by 21 and so on. And then he again subtracted. Then he got that half into 2 by 3x to be 1 plus 1 by 5 plus 1 by 7 plus 1 by 11. Now the trick is, now you see, earlier the first subtraction gave us a series in which the 2 and multiples of 2 are missing. In the second subtraction, we went one step further. Now no multiple of even 3 are also there. The first prime, we started this 5. So 2 and 3 are gone, and not only 2 and 3 are gone, all their multiples are also missing. So he extended the process further. Then again he divided by 5 and then subtracted to get the same, almost the similar pattern he got. Half, 2 by 3, 4 by 5, and the right hand side series is, it started with 7. Now the prime 5 and all its multiple has also gone. So the pattern was clear to Euler. At each step what is happening? One prime and its multiples are removed. We thereby generate a reduced series. The original series has been reduced to a series, and it started with 1 plus 1 by p. Where p, what is p? Where p is the next unaddressed prime. So undaunted by infinite processes. So this process has to be carried out indefinitely. So we now know that when the process is carried indefinitely, whatever happens for finite number of steps, it may not be true for the infinite number of steps. But then Euler is undaunted by this infinite processes, and he concluded that if we carry on this process infinitely many times, then eventually the reduced series will be left with right hand side will become only 1, because all the primes and its multiples will be removed. But what is all the primes and multiples? We, by fundamental theorem of arithmetic, we know that any positive integer greater than 1 must be divisible by at least 1 prime. So if I have to remove all the primes and its factors and its multiples, then every other number greater than 1 will be removed. So only will be left with this 1. So after that, he just finally, all we need to do is to find x from this. So he did the cross multiplication, and he got this identity where this is equal to x. So x is the infinite series. So this is how he reached the proof of this fact. You can say this is a manipulation of infinity. Some manipulations of infinity he did, but he did not realize at the time whether these are wrong or right. But eventually he got this identity. So from a modern perspective, this argument with its repeated operations on a divergent series is as porous as the sweet seas of Euler's homeland. Yet it has certain suggestiveness and undeniable appeal. Putting aside the questions of rigor, we see that Euler's powerful intuition has bridged the chasm between the harmonic series and the prime numbers, thereby giving birth to analytic number theory. So as I mentioned in the beginning, this is a harmonic series is an object of real analysis. And these prime numbers, they are the building blocks in number theory. So this formula has put a bridge on these two seemingly unrelated topics. And after Euler, this another mathematician called Riemann, he even went one step further. He has related number theory with not only real analysis, but with the complex analysis. And all the magic happened once Riemann introduced, related this number theory with complex analysis. So there are obvious logical shortcomings in the proof given by Euler, and those things were taken care of in 1876 by Leopold Kronecker. He actually modified the statement a little bit by introducing a real variable s. Instead of taking the series 1 by n, he considered the series summation 1 by n to the power s. And on the right hand side also, he has taken, instead of 1 minus 1 by p, he took it 1 by 1 minus 1 by p to the power s, where s is any real variable greater than 1. And then he has considered the case of Euler's result as the outcome of letting the limit of the variable s tends to 1 plus. Because s is strictly greater than 1, we cannot take limit as s tends to 1. So he considered, if we think of Euler, we can think of the Euler result as obtaining by taking limit as s tends to 1 plus. So it was Kronecker who introduced a real variable in this series. But Riemann went one step further and he took the variable s as belonging to the complex field. And he extended the function from real to complex, and then he was able to prove a whole lot of new results. So let us to give so our next aim will be to give a rigorous proof of this identity. So we now know that whatever proof was given by Euler, this looks nice, but it was actually not free from logical shortcomings. So our intention will be to give a rigorous proof of this fact, and then we'll use this identity to prove another fact that the number of primes must be infinite. So to do this, we must know something about the infinite sum and infinite product. Euler was not worried about the fact that the sum on the left and the product on the right were not convergent. So we cannot handle such series with such freedom as was done by Euler. So let us quickly review what is an infinite sum. So suppose we first define, let us what is we mean by a real sequence to converge. So if we have a real sequence of numbers, then we say that the sequence converges to the real number a if you give me any epsilon, and I can give you a positive integer n naught, such that the absolute value between a and a will be even less than that epsilon after some term onwards. That means after the n naught term, the absolute value of the gap between an and a, this should be made less than epsilon for any given epsilon. In that case, we say that the sequence an will converge to the number a. So we want to study mainly convergence of infinite series, but we can do that with the help of sequence only. So what if we are given an infinite series summation an, then from that we'll construct a sequence. By the sequence consists of what the nth term of the sequence is, the sum of the first n terms of the given series. So you just take the first n terms of the given series and name it Sn. And then you write S1, S2 and all those things. If this sequence Sn, if it converges in the above signs, then we say that the given series summation n, it also converges to that sum. The limit of the sequence will be called the sum of the series. So if the sequence Sn converges to a number S, we say that the series summation n converges to the sum S. Otherwise, we say that the series will not converge. Now for each n, the quantity summation n from k to infinity, the series was summation from 1 to infinity. Now if we fix any k, any positive integer k, and we consider the series from the k term onwards, so that will be called a tail of the series. And we have seen that the tail of a series which is convergent will be 0, will always go to 0. Because why? This summation n from n equal to k to infinity, it is nothing but the s minus sn, sorry, s minus sk. Because in s we have all the terms. So another important thing is, you see, this sum s, this sum also will denote by summation of 1 from n to infinity up to n. So the series and the sum, in case of the series is convergent, we both represent it by the summation n from 1 to infinity n. So here this s minus sk will be nothing but this. And since it is a the series is convergent, though this tail must go to 0. So this is a very standard result. You must have seen it earlier. And then we say that a series is convergent absolutely when if the series of, after taking the modulus, if you take the modulus of the individual terms, then if the series converges, then we say that the original series converges absolutely. Then a standard result is at every absolutely convergent series is convergent. So very standard result. Then the alternating series is an example of a series which is convergent. We will see afterwards that this series is called the alternating harmonic series. Because when the sum is all plus, it is called a harmonic series. When it is, the signs are alternately plus and minus, we call it the alternating harmonic series. So this is an example of a series which is convergent. We'll see shortly that this series is convergent. But this series is not absolutely convergent. That means if we add all the terms, if we replace the minus sign by plus everywhere, then this series will not be convergent. So such a series which is convergent but not absolutely convergent, we use the term conditionally convergent series. So for example, let us try to see that this alternating harmonic series is convergent. So this series is this, and then here the nth term of the series is an. An is 1 by n, because here the minus sign is absorbed here itself, minus n to the power n plus 1. So we are assuming all ans are positive. So this is a sequence which decreases because 1 is greater than half, half is greater than 1 by 3, 1 by 3 greater than 1 by 4. So the terms of the series decreases, and it decreases in such a way that the nth term 1 by n goes to 0. And since this is a alternating series, the terms are alternately plus and minus. So due to a famous test by Leibniz, so this series converges. So Leibniz test you must have seen, it applies to alternating series. The terms should gradually decrease and the nth term should go to 0. In that case, we say that the series converges. So the alternating harmonic series converges. So let us try to find the sum of the series if we can. So if Sn denote the nth partial sum of the series, then S of twice n, we are finding the sum of the first 2n terms. So here you see, it is a first 2n terms means this is a finite sum up to 2n. So we group the terms 2 by 2. So twice n is an even number. So we group the terms 2 by 2. Suppose 1.5 we are grouping, 1 by 3 and 1 by 4 we are grouping, and so on. So in that case, the sum will be k from 1 to n, and then this is the odd term, and this is the even term. And then, you see, if we rearrange this slightly, if you make it plus here and then 2 times I can subtract it, it will remain an equality because it is a finite sum. Any manipulation in finite sum is very much okay. So in that case, what I'll get, you see here, if I combine these two terms, earlier you see terms are minus and plus, but now I have made all signs plus. So I am getting one odd term, one even term, up to n terms, up to n. So since 2 terms are there in one bracket, so basically I will be getting the harmonic series with all the plus sign up to twice n terms. So this is the sum of the harmonic series of the first 2 n terms. And here these 2 and these 2 can cancel. So I will be left with the sum of the harmonic series with twice n terms minus sum of the harmonic series up to n terms. So what I will be permanently left with, sum of the from the n plus 1 term to the twice n term. So by a change of variable, in place of k starting from n plus 1 to twice n, I can start with k equal to 1, then this will be n plus k. Same series will get. So then you see this limit. Now since you see, I already know that the alternating harmonic series converges. So that means the sequence Sn converges. And we know that when a sequence will converge, any subsequence of that series will converge to the same sum. So since we in advance we know that the alternating harmonic series converges, so even if this is a subsequence of the sequence of partial sum, whatever was the limit of the subsequence, this will also be the limit of the whole sequence. So it is enough for us to find the limit of S twice n. So in this case, it is important to know that in advance that the series converges. So if I take the limit here, then I find this. This I have multiplied numerator and denominator by k. And if you now remember the formula for integral as a limit of sum, so this is nothing but the integral from 0 to 1 of the function x plus 1. So in the integral of a limit of sum, you have to make it a function of n by k. So if this k in the top, if we divide both numerator and denominator, I will be get n by k plus 1. So every n by k should be replaced by x. So I will be left with the integral of 1 by x plus 1. And if I integrate it, this is log of x plus 1, and then log 2 minus log 1. This log 1 is 0. So we are again getting log 2. So the sum of the alternating harmonic series is logarithm of 2. Then let us now try to see that even though the alternating harmonic series will converge to the sum log 2, the harmonic series is actually not convergent. But it was believed, for many centuries, it was believed that the harmonic series actually converges. The main reason of the belief is that even on a computer, if we want to get a sum 100, we need to add 10 to the power 43 terms. So what is the meaning of a series is not convergent? A series is not convergent means it can sum to any given number. So whatever number you can imagine, I can take enough term from the series so that the sum of those terms will give me that number. But here, in case of this harmonic series, if I give a relatively small number 100, then even to get the sum 100, you have to consider as many as 10 to the power 43 terms. So people believed that this actually sum is actually finite. But it was proven later that this series is actually not convergent. So how to see this? So this is a very simple proof. Suppose Sn is the sum of the first n terms. Then what will happen to this S2? This S2 is the sum of first 2 terms. So this is nothing but 1 plus half. The first 2 terms I have taken only. And then what is S2 square? This is the sum of S4, means sum 4 square, sum of first 4 terms. So the first 2 terms is already there, then the third and fourth term. But this first 2 terms is already 1 plus half, and this third and fourth term are also less than half plus half. So this term also I can make it this 1 by 3 plus 1 by 4. This is also greater than half. So this sum is actually 2 by 2. This 1 plus 1 is 2 by 2. Similarly, if I take S2 2 cube term, if you find S2 cube, you will see that here 3 will come. So by induction principle, we can see that if I take S of 2 to the power n, then it will be actually greater than 1 plus n by 2. This here, you see S2, I getting 1 by 2, 2 to the power 1. S2 means 2 to the power 1, so 1. S2 square, so 1 plus 2 by 2. By induction, we can show that this S of 2 to the power n will be greater than 1 plus n by 2. So this inequality is enough for us to conclude that this sequence cannot converge, because this right hand side 1 plus n by 2, this will go to infinity. So this S of twice n is in fact bigger than this. So this subsequence S twice n, this will also go to infinity. So this sequence Sn cannot converge. So as a result, the harmonic series cannot converge. So we have given an example of the alternating harmonic series which will converge, but not the harmonic series. Even though the convergence, even though it goes to infinity very, very slowly, but still it goes to infinity. Okay. Then let us see. Okay. So let me just ask you a question. So is everything going on well? Am I audible very clearly?
Yes, sir. Very clear.
Yeah. Or should I go a little bit fast, or is it okay?
This is fine, sir. The pace is
Fine.
good.
Okay.
Yes.
Okay. So I'll try to finish in another half an hour. So let us see.
Fine, sir. Fine.
Yeah. So let us try to see how grouping of terms affect the sum of the series. In a finite case, you see, if a finite number of quantities we have to sum, then in whatever way we group the terms, grouping means actually putting brackets in some specified intervals. So in adding finitely many quantities, where you put the bracket is immaterial. But in an infinite series, let us try to see whether we can put bracket at will or it will affect our sum. So suppose we have an infinite series an, and we have some real numbers b1, b2 up to b and so on, which are related by this. So what is b1? b1 is the sum of the first n1 terms. So that means we have given a bracket after the first n1 terms. Then the next n2 terms. So up from n1 plus 1 to an2 terms, we have given another bracket and name it as b2 and so on. So that means we are putting bracket in between terms. Then we say that this new series summation n from 1 to bn, this is obtained from the original series n by grouping of terms. So for example, in the earlier case, you see here where we have grouped. So here this one between 1 and 1.5 we can put a bracket. Between 1 by 3 to 3 by 4 we can put a bracket and so on. Here we can put bracket after every 2 terms or after every 3 terms or first after 3 terms, then after 4 terms, then after 8 terms. There is no pattern. We can put bracket anywhere we like. So such a series is said to be obtained from the original series by grouping of terms. So the result is how does grouping affects the convergence of a series? So the result is that if a series is known to be convergent in advance, suppose we know the series to be convergent, then you can group the terms in any manner, whatever you like. The resulting series will have the same sum. So grouping of terms does not affect the sum of a convergent series. So that is a very good result. So as long as the series is convergent, you can group the terms in any manner as you like. But in general, grouping may change sum. For example, you see this series everybody has seen 1 minus 1 plus 1 minus 1 and so on. So if you give bracket after every 2 terms, then every factor becomes 0. So obviously it will go to 0, its sum will be 0. But then if we leave the first term aside and put bracket after 2 terms from the second term onwards, so that means 1 I am leaving it extra, then I am putting a bracket on the second and third term, then 4th and 5th term and so on. Then what will happen? Then the first term will become 1, other terms will become 0. Then the sum will obviously be 1. So in a random series where we do not know about whether the series converges or not, we are not allowed to put bracket at will. But as soon as we know that the series is convergent, then a general theorem is there. You can put bracket, the sum will not be affected. Then when can we actually say that after putting bracket, the next line say what it says? Suppose a series Bn has been obtained from n by grouping of terms. Then this resulting series will be convergent. So what we actually basically wanted to say, so in the first line, the first item, what we have said, so if the series is convergent, then you can put bracket, the resulting series will remain convergent. In the second item, what we have seen, in a general series is given to you, if you put bracket, if it becomes convergent, you cannot say whether the original series is convergent or not. Because this 1 minus 1, if I put bracket, the resulting new series become convergent. But the original series is not convergent. Now the question is, can we say that if the group series is convergent, can we say that the original series will also be convergent? Then this answer is given in the next item. So suppose the group series is convergent. After grouping of terms, a series become convergent. Then you can say that the original series is convergent provided the term in the group series, the nth term Bn, you take the absolute value of each of the terms. Then if the sum still goes to 0, in the nth term, after putting absolute value, if it goes to 0, then you can say that the original series where there is no grouping, that will also converge. You see, this is not true in case of the second item. In the second item, you see, this is my B1. What is my B1? B1 is 1 minus 1. B2 is also 1 minus 1. B3 is also 1 minus 1. So Bn, nth term is also 1 minus 1. So his 1 minus 1, you can say that it goes to 0. But as soon as I put absolute value individually, in 1 minus 1, if I put absolute value in each term, then it becomes 2. So 2 will not go to 0. So that is why this third item is not applicable for the second. So grouping of term is allowed for convergent series, but if the series is not convergent, we have to take proper care to group terms. Otherwise, we may get impossible results. So let's move to another important part of the series, what is called the rearrangement of series. So what is a rearrangement? Suppose you have a series An, then you have another 1-on-2 map. Then you reshuffle the terms of the series according to that map, F. So An is replaced by Fn. What is Fn? F is a bijection from n to n. So basically rearrangement is what? You are allowed to reshuffle the terms, but you cannot repeat the terms. One term has to be used only once. It has to be in a 1-1 fashion. So you can reshuffle. The second term can be made to first, the first term can be made to seventh, and so on, in a 1-1 fashion. Then it is called a rearrangement of the original series. For example, you see this, if we consider alternating harmonic series as S, then this series T is what? We have written here two positive terms. 1 plus 1 by 3 we have written, and then we have taken the second term, that is minus half. Then again two positive terms we have written, 5 and 7. Then again one negative term we have written. So in this way, we have written every term of the original series S only once, and we have not dropped any term. In a 1-to-1 fashion, we have related. So this T will be called a rearrangement of this series. So what we were going to see, that we have just seen that grouping of a convergent series does not affect the sum. If the series is convergent, you can group it in any manner, it will not affect the sum. So now we are going to see that this is not the case in case of rearrangement. Even if a series is convergent, still you cannot rearrange the terms without affecting its sum. Once you rearrange, its sum may be affected. So to see this, we have taken the example of the alternating harmonic series. We have proven that this alternating harmonic series converges. But we shall see that if we rearrange this, just like this T, this S and T, they will not have the same sum. This T is a rearrangement of S, but we'll see that the sum of S already we know. This is log of 2, we have proven. But we'll see that the sum of t is not log of 2. It will be something else. So let us see. So what we are using? So we are using the fact that if a series is known to be convergent, and if we multiply this series by any scalar, so it will remain convergent. And the sum will be that scalar times the original sum. So this is a very simple basic fact. And then we also use the observation that if you insert any number of zeros anywhere in a series, it will obviously not affect the sum, because as many zeros as you add, you will get 0 only. So we can insert 0 anywhere we like. So in view of this, we can write this as, if we multiply by half, we'll get this series. We have multiplied both sides of the alternating harmonic series by half to get this. And then at odd places, we have included some zeros. At the odd places, first, third, fifth, we have included some zeros. So these zeros are not going to affect the sum of the series because they are after all 0. Then what we will do? We will add the series S with the series half S. This is perfectly allowed because you have seen the result that the sum of two convergent series is convergent, and their sum is sum of the two original series. So using that result, since these two series are convergent, we can add them. So if we add them, what we'll get? We get 3 by 2 of S, and then if we add them term by term, what we'll get? 1 plus 0, then minus half plus half, 1 by 3, 0. And if we rearrange the terms, what we get? 1 plus 1 by 3, it is exactly the series T. So it is exactly the series T. So the series S has the sum log 2, but this series T, this will have the sum 3 by 2 of S. That means 3 by 2 times of log 2, log of 2. So even if we have rearranged and we have done all the valid operations, this rearrangement did not preserve the sum. So this shows that the convergent series S has the sum log of 2, whereas its rearrangement T has the sum 3 by 2 of log. So the rearrangement of terms in a convergent series does not necessarily yield the same sum. Then the question arises, so are we not allowed to rearrange terms? So can we not rearrange the terms in any convergent series? So there is some relief which says that this query is answered by this question. So what is this? The first slide says what? So suppose we have a conditionally convergent series, just like the alternating harmonic series. So what we are able to do? We are able to rearrange the alternating harmonic series to get a sum 3 by 2 log 2. Originally it was log 2, but now we can rearrange to get a sum 3 by 2 log 2. But this was a famous rearrangement theorem of Riemann, which says that if the series is conditionally convergent, that means it is convergent but not absolutely convergent, and S is any given number, anything, any real number you can give, then I can make a rearrangement of this series AN so that the new rearranged series converges to S. So the last example is only a particular case where I have been able to rearrange the series to get the sum 3 by 2 log 2. But not only 3 by 2 log 2, I can rearrange the sum to get the sum 5 also, any real number. So this is a very strong and powerful result of Riemann. Not only that, Riemann proved that there also exists rearrangement that either diverges to plus infinity or minus infinity. I can rearrange the series in such a way that it becomes diverges to infinity or even diverges to minus infinity. Or it can oscillate. It will neither diverge or it will not approach to any limit, finite or infinite. So all possible behaviors are possible for a conditionally convergent series. However, on the positive side, if the series is known to be absolutely convergent, then nothing of that sort will happen. If the series is absolutely convergent, that means even after putting modular sign on the terms, if the resulting series converges, then whatever rearrangement you do, it will give you the same sum. So just like in the grouping, there is the same sum, but in case of rearrangement, convergence is not strong enough to assure this. But if it is absolutely convergent, then you can be rest assured that the sum will not be affected even after the rearrangement. Okay. Then let us try to to go towards a proof of the rigorous proof of the your Riemann this Euler's theorem. So we saw that the series 1 by n to the power s is not convergent. Sorry, summation 1 by n is not convergent. The harmonic series is not convergent. But some magic happens as soon as we introduce a new real variable s, which is greater than 1. Which is greater than 1. So you can easily check that if s is less than 1, then if we compare this series 1 by ns with 1 by n, so this 1 by ns will be greater than 1 by n. When s is less than equal to 1, this 1 by ns will be greater than equal to 1 by n. So the sum of this series will be greater than the harmonic series. So the harmonic series even goes to infinity. So this will also go to infinity. So this 1 by n to the power s series, when s is less than equal to 1, will obviously go to infinity. It is not converged. But we'll now see that if the variable is greater than 1, then this will always give you a finite sum. So that is a very, very important result. So what is the importance of s greater than 1? You see that as soon as s is greater than 1, then if you take two positive integers m and n, the bigger the integer m, the bigger will be the power, because s is greater than 1. So if we use this fact, then after the first term, the second term is 1 by 2s, third term is 1 by 3s. So this is less than 1 by 2s plus 1 by 2s, because 3s is greater than 2s, so 1 by 3s will be less than 1 by 2s. So this is 2 by 2s, so 1 by 2 to the power s minus 1. And then we group the next four terms. Here we have grouped the first two terms. In the second case, we are grouping four terms. Then one question can come to your mind that we can group terms in a convergent series only. But we are trying to prove that this series is convergent. So how can we group here? So the answer for that is that we are not grouping in the infinite series. We are only grouping finitely many terms. So here we have not yet grouped. Here we are just using an inequality using four terms. So these four terms is less than the first term multiplied 4 times. So this is, I can write as 1 by 2 to the power 2 square s minus 1. So now see this, the partial sum Sn. So in this case, this s to the power k, here sum of 2 terms, here sum of 4 terms. So here I am allowed to group because s twice k is a finite sum. It is not the series. It is a sum of the first 2k terms. So in this finite, I can group whether convergent. In finite, there is no question of not convergent. Everything finite is convergent. So if we group the terms like 2, 4, 8, 16 like that, and I use the inequality, so what I get is this. This is the geometric series with common ratio 1 by 2 to the power s minus 1. So its sum is 1 by 1 minus the common ratio, which is this. So this is right hand side, there is no k. Right hand side, there is no k. This shows that this partial sum, the sequence of partial sum s to the power twice k is bounded above. So see, now given any n, I can always find some k such that n is less than twice k, because the set of positive integers is unbounded. So however bigger number integer you take, there are still bigger integers. So using this fact and the fact that Sn is increasing. Why is this Sn increasing? Because this Sn is a sum of positive terms. All our terms are positive. So the more number of terms we are adding, the more bigger number we are getting. So the sequence of partial sums of any positive series is always going to be increasing. So since this is increasing, we have this result. This Sn will be less than this, and this is less than this. So this shows that this Sn, the sequence of partial sums, is bounded above. So the sequence of partial sum is bounded above also, and it is monotonically increasing also. So this must be convergent. This sequence Sn must be convergent. So if the sequence of partial sum is convergent, the resulting series must be convergent. So this series converges for s greater than 1. And since this is a series of positive terms, so this is actually absolutely convergent. Absolutely convergent means after putting modulus also, it should remain convergent. But since it is of positive terms, putting modulus and not modulus are the same thing. So this infinite sum, even though the harmonic series is not convergent, after putting a variable s which is bigger than 1, this has become convergent. Okay. So now let us move to infinite product. So infinite sum more or less we have studied in your undergraduate course, but this infinite product is not studied with much detail. So let us try to see what we can. So obviously we'll try to relate product with sum. So you must have studied your in your school level what is a logarithm. So logarithm is a way to convert product to sum. So you know that once you have a product AB, once you take logarithm of both sides, it becomes a product log of A plus log of B. So product can be always converted to sum. And since we already know about infinite sum, so we expect to relate infinite product with sum also. So keeping the analogy with the sum, so suppose we are given a sequence of real numbers. So we want to, how we define infinite series? So infinite series was defined. First we define a sequence of the partial sums and then the limit of that. So here, so what it will be tempting to define first the partial product. In place of sum, Sn, we have taken Pn. Pn is the partial product, means the first product of first n terms, and then take the limit. And try to say that if the limit exists, then the product will converge, otherwise not. So this is our obvious way to extend the concept to product. But there are some problems in this. The problems are what? Suppose this definition would be inconvenient, since every product having one factor equal to 0 would converge to 0. So if we allow this without any restriction, so what happens? In case of sum, we do not have that problem. If one term is 0, then the sum will not be 0. But in case of product, even if one product is 0, all the product of all the numbers will be 0. So that means we have to say that whenever one term is 0, then whatever happens with the other terms, the product will converge to 0. But this is somewhat unwanted, because in case of series, we have seen that whatever happens to a series depends on the tail of the series. Tail means you remove the first few terms, whatever happens towards the end. So that is the actual behavior of the series. But here you see that if you take the first term to be 0, and whatever you take the remaining terms, the product will be 0. So this is somewhat undesirable. So we do not want this to define our infinite product as it is. Some modification is required. So another thing what we want, that we also expect that whenever the product of the series Sn, An goes to 0, will converge to a number, we want that the infinite product of their inverses should also go to R inverse. So just like you see, if 6 into 3, so if some series converges, 1 by that series, it should also converge to 1 by that number. So that is also somewhat we want. But that will not be also possible. So even if some ANs are non-zero, just like we have seen that the limit can be 0. But if limit can be 0, then what will happen to this 1 by 0? This 1 by 0 will become undefined. So some problem is there when the limit becomes 0 or when the terms are 0. So there are two cases we have to take care. What will happen if some terms of the series or the sequence AN are 0? And what will happen even if none of the member AN is 0? What will happen if the their product of Pn, the sequence of the partial product goes to 0? What will happen in that case? So these two facts we have to take care. So let us, with keeping with this mind, we try to define infinite product like this. Suppose none of the factor is 0, and suppose the partial product goes to a number, it converges to a number P, where P is non-zero, because 0 has some problem we have seen. So in that case, we will take it as the ideal case. There is no problem, that original definition stands. So in that case, we say that the product will converge to P, because the problematic case are when some terms are 0 or when the limit is 0. If neither of these happens, then we have no problem with the earlier thing. So this stands. So Now see what may happen if none of the term can be 0, but the limit may turn out to be 0. The limit may turn out to be 0. In that case also there will be a problem. So in that case we do not say that this infinite product converges, but we say that this diverges to 0. When the none of the factor is 0, but the limit of the partial product is 0, then we say that the product diverges to 0 instead of it converges to 0. And then what may happen, now take care of this case when some of the terms are 0. Suppose finitely many of the terms n are 0. If finitely many are 0 means what will happen? After some stage, after some terms, there will be no zeros. So whatever the maximum, wherever the 0 at the maximum position, so that positive integer n we are taking, then what you can say, after n greater than n, none of the n should be 0. So in that case, what we will do? We will define this product in terms of this product. This first term we will ignore. This first n terms we will ignore and we will consider the product n from n plus 1 to infinity n. If this product converges in the above sense means here none of the term is also 0, and if it converges to some non-zero number, we will say that this product converges. Or if it converges to 0, we will say that this product diverges. But then you can question, we are not willing to define this product. We are willing to define n from 1 to infinity. In that case, what will we do? In that case, the value of this product n from 1 to infinity, we will be defining this finitely many terms, we will multiply. And then we will multiply this result with the product from n plus 1 to infinity. So this is actually same as summation n from 1 to infinity. So if these terms are 0, obviously the product will converge to 0, because whether this product is non-zero or 0, if these terms are 0, then the product will be 0. So this shows that infinite product can converge to 0, but only when some of the terms are 0. Some of the terms are 0, otherwise no. Then we are left with the case if infinitely many n's are 0. If infinitely many terms of your sequence is 0, then we say that the product will not converge. Then we define the product to be diverges to 0. Okay? Not, I think it is, diverges to 0, because if all are 0, product will be 0. Yeah. So note that the value of a convergent infinite product can be 0. But this is possible only when finitely many factors are 0. Because if this a1, a2 up to an, if sum of the term is 0, so even if this product n from n plus 1 to infinity is non-zero, so this 0 into something will be 0. Okay. So let us consider two examples. First example is the infinite product of 1 plus 1 by n. So in this case, if we multiply the first n terms, so this will be what? Pn will be I from 1 to n, this 2 by 1, 3 by 2 up to n plus 1 by n. So if I simplify this 2, 3 all will be cancelled, we will be left with n plus 1 by 1. But this n plus 1 by n, this n plus 1 goes to infinity. So that means the partial product goes to infinity. So that means this infinite product cannot converge. In this case, this diverges. The second example you see, we have taken n from 2 to infinity, 1 minus 1 by n. 1 we have not taken because if we put 1, 1 becomes 0. So the first term will become 0. So we do not want such case. We want a product where none of the term is 0. So in this case, what is the partial product? It is, if I simplify, it is n minus 1 by n. So it is 1 by 2, 2 by 3, n minus 1 by n. So it will be it simplifies to 1 by n and it will go to 0. But since the limit is 0, in this case also we will say that the product is not convergent. In fact, it diverges to 0 because the limit is 0. Yeah. So some of the properties. So what is the first property? If the infinite product converges, just like in the sum of series, if a sum converges, the nth term goes to 0. So similarly, in an infinite product, if the product converges, then this nth term must go to 1. Because this n is nothing but the nth partial product divided by the n minus 1th partial product. And since both of these go to a limit which is non-zero, suppose the limit is L, so this will go to L by L and this will be 1. So that is why it is important that L should not be 0. Otherwise this result also will not get. So equivalently, when since the limit each n goes to 1, so we can replace this term an by some 1 plus, these ans are near about 1. So I can replace the product terms by 1 plus some an. So in that case, this an will go to 0 because this 1 plus an has to go to 1. So an must go to 0. So two very important results. So if the product will converge if and only if the sum converges. Just like I mentioned in the beginning, this logarithm part. So a product converges if and only if the sum of the logarithm converges. So in that case, we have to be careful because since logarithm of negative numbers is complex, so we have to take care, we have to restrict our case to series where the terms are positive. Otherwise, this logarithm will not make sense. Okay. Similarly, if the infinite sum converges absolutely, if we know in advance that a sum converges absolutely, then this product 1 plus minus an, this will also converge. So this is a relation between sum and product. By knowing that the sum an converges absolutely, I can know that the product 1 plus an converges. So with these all things, we can now take the right hand side, the infinite product in the Euler's identity. We can show that now this product also converges. So how to show that this product converges? We'll use this result. If the sum of the series an converges absolutely, then the product will converge. So here you see the sum, we have to take care of this term, p to the power minus s. But what is p to the power minus s? This is 1 by ps, but this is less than 1 by ns. Because this is the sum over all the primes, and this is the sum over all the integers. So obviously this sum will be bigger. But we have already seen that this series converges. This series converges 1 by ns. So that means this series also converges. So since modulus is there, these terms are positive. So this series converges absolutely. So by the earlier theorem, so since this series converges absolutely, this product also converges. And this converges is absolute because all the terms are positive. All the terms are positive here. And as a result, this product converges absolutely because the terms are all positive. Here, these two are not the same because here there is no 1. If the product converges, 1 by that product also converges. So here you see 1 by is there. So from this line, we have used the result that if a product converges, then the inverse of the product converges to the inverse of the original limit. So we are able to see that in the right hand side product, in the Euler's product formula also converges. So we can now give a rigorous proof of the Euler product. So you see, we have seen that, we have justified that this sum also converges absolutely, and just now we have seen that this product also converges absolutely whenever s is greater than 1. Then, since s is greater than 1, this p to the power p is a prime, p to the power s is also greater than 1. And therefore, p to the power minus s is less than 1. And therefore, this quantity on the right hand side is a geometric series. It is the sum of the geometric series 1 plus 1 by ps plus 1 by p2ps and so on. Okay. Now for a fixed prime p, q, by fundamental theorem of arithmetic, if I multiply, you see this is the partial product of the infinite product. Here we have multiplied up to a prime q. Q is a fixed prime. So this is a finite product now. So if I expand, so this term, just now we have seen that this term is a series like this. So if I rewrite the series for each of the q terms, here finitely many terms are there. And if we multiply out these terms, suppose 1 into 1, 1, so this 1 term will come. This 2s will come. Why? Because this 1 by 2 to the power s is there. And all the 1s I will take. In every series, there is a 1. So then 1 by 2s will get. 1 by 3s will get because this second series will be. Hello? Hello? Is there anything?
So just continue, sir.
Yeah. So the second prime will be 3. So 1 plus 1 by 3s will come. So if I take 1 from the every other bracket and 1 by 3s, then I will get this. Then you may tell where from this 6 or 4s will come. Because 4 is not a prime. 4 is not a prime, but still 4 will come because this 2 to the power 2s. This is nothing but 4 to the power s. So then can we see how 1 by 6 to the power s will come? 1 by 6 to the power s will come because 1 by 2 to the power s will be from here, 1 by 3 to the power s will be from the second term. If we multiply these two, I'll get 1 by 6 to the power s. So here we are using the fundamental theorem of arithmetic, because every positive integer can be obtained as a prime product of prime powers. So all primes are here. So every positive integer will be written uniquely once. But in here I have got all the numbers up to q, but there will be more numbers will be here. But I have ignored this number and put the greater than sign. So I am getting the sum of n from 1 up to q, 1 by n to the power s. So now if I subtract from the, this zeta s, I have not used the symbol earlier. This is the sum of this series. This is the sum of this is actually the sum. So this is the shortcut notation I am using for this. Yeah, I have written here. So zeta s is the sum of all the terms. But this here, I have the sum up to q terms. So if I subtract this, what I'll get? I'll get from the q plus 1f term to infinity. And because of this modulus, and this is greater than, so if I subtract, it will be less than this. And now since this is a convergent series, 1 by n to the power s, and this is a tail. This is a tail of the convergent series because it starts from q plus 1. And we have seen that the tail of a convergent series goes to infinity as this variable goes to infinity. So we have proven that when the number of primes goes to infinity, these two will be the same because this goes to 0. So this is exactly the proof of zeta s equal to product over all the primes of this. So this is the rigorous proof of this. So we have arrived to the final part of the thing. The final part is we want to say that so that the number of primes is infinite using this product formula. Okay. So first of all, let us see that I want to take the limit of both sides, and because this identity is valid. This identity that these two are equal, this is valid only for s greater than 1. Only for s greater than 1, this is valid. So I want now to take the limit as s tends to 1 plus. So this is this zeta s value I have put, and here I have written up to any number x. Suppose I have fixed a positive real number x which is greater than 1, and this is the sum of all series. And here I have written up to terms up to x. So obviously this will be bigger. And since my s is greater than 1, so I am taking a limit as s tends to 1 plus. And since this is a finite sum now, so I can take the limit inside. So then it will become 1 by n. In an infinite series, I cannot take the limit inside here. But since this has become finite now, I can take it inside the summation sign to get 1 by n. So what I have got, that limit s tends to 1 plus zeta s is greater than equal to the sum of the harmonic series up to the x term. Now you see, this inequality you see, this logarithm of x is nothing but the integral of 1 to x dt by t. Because dt by t is log of x and then the variable is 1 to x. So log x minus log 1. So this is log x. Log 1 is 0. So I can break this integral as sum of these n integrals 1 to 2, 2 to 3 and so on. Now I want to estimate these integrals. You see, in this first integral, your t is varying from 1 to 2. So t will be greater than 1. So 1 by t will be less than 1. So that is why this will be less than equal to 1 dt. Similarly here in the second integral, t is greater than 2. So it will be 1 by t will be less than half. So this is less than equal to half dt. And so on. This will be 1 by n. Now all these lengths are 1. Length of the integrals are 1. So this will be 1 plus half plus. The last will be 1 by n minus x. But this x is just above n. So this n minus x is also less than 1. So this, we are getting this. So this is nothing but the right hand side of this. So log x is less than equal to the sum of the first n terms of the harmonic series. So what it gives, if we combine these two items, we get the limit s tends to 1 plus zeta s is greater than the sum of this series, and which is greater than equal to logarithm of x. But our aim is to show that this limit is infinite. So now after proving this inequality, it becomes easier because log x goes to infinity. Log x increases to infinity as x tends to infinity. Why is it so? Because it is well known that logarithm function is a increasing function in 1 infinity. Because the derivative of this logarithmic function is 1 by x, which is greater than 0 in 1 infinity. So this is an increasing function. And then what will happen? If you give me any positive integer n greater than 1, I can choose a real number sufficiently large. It is greater than e to the power n. And then since log x is increasing, I can take log on both sides to get log of x will be greater than log of e to the power n, which is n. So you see what I have achieved. You give me any n greater than 1, this logarithm of x is even greater than n. So since n is arbitrary, it says that log x will go to infinity as x tends to infinity. So the outcome is what? This limit, which is bigger than log of x. So this will also have to be defined. So finally, this right hand side product, the terms are 1 minus p to the power minus s. So since s greater than 1, so this is less than this. This is less than this. Now, suppose my aim is to prove that the number of prime is infinite. Now, if the number of prime is only finite, then the product, infinite product will become a finite product. Infinite product will become a finite product. Then if I take the limit, and then this limit can be taken inside because it is a finite product only. And then this will be less than this quantity. And since none of these are 0, only finitely many quantities are there, so this will also be finite. So what we have achieved, if the number of primes is finite, then in the Euler's product formula, the right hand side is a finite quantity if I take limit as s tends to 1 plus. Whereas I have shown that the left hand side, the infinite series, it goes to infinity as s tends to 1 plus. So this will give me a contradiction because one side is infinite, one side is finite. There cannot be any equality. So the number of primes cannot be finite. So this will leave me a contradiction. So this is what I wanted to say. And these are some of the books that I have used while preparing the slides. So you can go through these books. These are books which can be read by with a minimal background. Any undergraduate student will be able to go through these books. These books on analysis by Apostle. So this is a standard analysis book that is taught in the undergraduate. So for infinite product and infinite sum, all the materials I have taken from this book. So thank you. With this, I'd like to stop my lecture. So if I have any question, I'll be happy to answer.
Okay. Wow, that was an interesting topic. And then thank you so much, sir. And then I believe that your talk has given some spark to the students, and then which will definitely take them to some greater heights, especially in terms of research in number theory. So now I'll hand over to Mr. Sedeviko for the Q&A.
Thank you, sir. It was such an interesting talk. You have started from the very basic things of prime numbers, the proof of which we all know, and then you took us to some very interesting talk, and then like those harmonic series and all things. You made some very interesting comments on those things. So thank you so much. From participants, if you have any questions, you can type in the comment box, the chat box, or no questions. Okay, so from the participant sides also, we don't have much questions, nor in the this one YouTube link also in the chat live chat of YouTube link. We don't have any much questions. If there is any question from student side, you're most welcome to ask.
Hello.
You can even mail me in a mail ID.
Hello. I don't have the question, but just I want to say that it's a very informative talk. I really enjoyed it. Whole session I was sitting here. And not only me, all the colleagues were sitting and we were watching this your talk, and I believe that surely it will benefit even from the BSc first semester students up to the MSc, and even the students who are pursuing their PhD in this topic, number theory. So really it is very informative, and it was important talk for today. So thank you, sir, from my side. It is very good talk you have delivered today. We'll surely will need your help in the near future. Again, thank you once more.
Yeah. So thank you again.
Sir, would you be kind enough to share your slides with us?
Yeah, sure. So should I mail or what?
Yes, sir. Please, you can mail it to us. And then, sir, do you have any books that you recommend for us or students to follow?
Yeah, I think I have given these books that I have listed here.
Yes.
So in this area, if you want to study this first author, this William Dunham, so he has actually written some 3-4 books I have seen.
I see.
So these are all related to the history or the interesting topic which can be understood by the undergraduates even. So in a very interesting way, he has written. Some 3-4 books are there. Just like here, the Euler, the master of all. So whatever mathematics Euler has done, so many things he has explained in a way that can be understood by a beginning graduate and undergraduate.
Yeah. Thank you so much,
So
sir.
the other books by this Mazur and Stay. This Mazur is a field medalist. He's a very big mathematician. But these books, this prime numbers and Riemann hypothesis, he has written in a very easy way for the undergraduate student without using heavy mathematics. He has written for the undergraduates. So I think these books can be seen. Yeah.
Thank you so much, sir.
Okay.
Yeah, from
so I can stop sharing now?
yes, sir.
Yeah. Let me stop sharing my slides.
And yes, sir. Can you remember to mail us your
sure.
slides? Yeah.
Actually, sir, Pandey sir's mail ID I have. So in that mail ID, I'll surely.
Okay, sir, please. Yeah.
Yeah.
So
thank you then.
there is no question from the participant side. I think you have made things clear enough for all of us.
Yeah.
Thank you so much, sir, for your valuable time. And then we look forward to work with you in future also. Yeah.
Okay. Thank you.
Thank you so much. And over to Bendang
Have
again.
a good day. Yeah, have a good day.
Thank you, everyone. So now I should say the most important part. That is the word of thanks. So to pronounce the word of thanks, I would especially like to thank the following individuals, especially our principal, Dr. Lily Sema, for allowing us to host this program, and then a very grateful gratitude to the two resource person, Dr. Ankur, who had delivered his talk on linear algebra and its application in data clustering, and also a special thanks to Dr. Naba Sharma for his talk on infinitude of primes using infinite products. Thank you, sir. And then we are very thankful because in spite of your heavy schedule going on with your teaching and then even with your online teaching, you have spared so much, and then hats off to sir. And then you have been sitting from the beginning till the end. And so hats off to you, and then thank you so much. And then we'll be looking forward for your assistance in the near future also. And then I believe you won't be reluctant in accepting our invitation. Thank you so much. And then I would also like to take this privilege for thanking the Department of Mathematics, and then for allowing me to coordinate the program, and then convey my thanks to all the all the individuals who has taken part in the program, and then especially those who are taking part in the back, behind the scene people also. I would like to thank them. And then finally, I would like to thank all the participants, those who have participated from around the globe. And then it is because of you that it has made this webinar successful. Thank you so much. And then I believe that this webinar has benefited every one of us, including me. It was very beneficial and very informative. Thank you so much. Let's hope to see each other in more webinar of this form. Thank you so much.
Thank you.
Thank you so much. Okay, so the feedback link has been provided. So, and then like our HOD has mentioned, we will not be able to provide the certificate to the faculties as the target of this webinar for the students only. So we'll be providing the certificate to the students, those who submit the feedback submit the feedback. So I've provided both in the Google Meet as well as the YouTube. So thank you so much. And thank you so much, sir.
Thank you. Thank you.
Okay, we'll end it here then.